So, all right, so I guess I'll go back and forth from the prelim to whiteboard. Yeah, so I think everyone did problem well. I'll just go through all of them. Not to. I'll go quickly with the ones everyone did well on. So yeah, everyone did fine. Problem one. Also, yeah, go through it just for anyone who wants to, who's taking it in August and wants to see this. So yeah, easy dominate convergence theorem problem. One. Second. Okay. Yeah, so do what everyone did. Just set fn of x be characteristic function of n infinity of f. So for all x, I guess technically these are only defined for almost every x. So it's technically for almost every x, but it doesn't matter on the prelim. Yeah, so this is kind of trivial. It's 0 away from 0 to 1. So 0 is less than or equal to whatever absolute value of f is. So this is my dominator. We're assuming f is an L1. Again, technically, f is only defined almost everywhere, whatever. Certainly this is true. So yeah, easy dominate convergence theorem. Move that down a bit. We'll take dominate convergence theorem. This limit here is this limit here. Is 0. So easy peasy. Any questions on this? No. All right. All right. So number 2. So forget when. I know it was a long time ago this was on, but I think this was put on more recently. Or at least kind of if and only if was put on a while ago. I think more recently. So kind of half of the old prelim problem. Yeah, if this is true and the EN's partition A, then prove that each EN is measurable, right? So maybe it's actually better. Let me do this. Let's paint. So keep this up. Go. Okay, so 2. We'll just remember what we need to do. let's fix an N0, whatever you want to call it. So as always, we need to show that for any A, this here is bigger or equal to A intersect En0. So remember, trying to show that this one here is measurable. So what I'm trying to do. And here's the complement. The other direction is always true from subadditivity. So that's what we're trying to do. Okay. Probably easiest thing to do is just and sorry, this is outer measure is we don't know if A is measurable and we don't know if E is measurable. En rather, En0 is measurable. En not. So yeah, let's just use what we're given. And this is true for any A. And then do kind of the obvious thing, which is down a bit. Break this up into A intersect 0, and then N is not equal to N. Yeah, it's definitely a good idea because all I need to do is connect these two. Particularly, I need to show this is bigger or equal to this. Right. All right, so I'm going to use partition property in a minute. Let's have some more room. Any questions so far? Right, so yeah, so actually let me first use countable subadditivity. So the ENs are pairwise disjoint, but we don't know if anything is measurable at all, so you cannot use countable additivity. We always have countable subadditivity. And it's going in the right direction, bigger or equal to. Stuff here. Right. Great. All right, but you can write A as this yeah, so let me do it like this. Yeah, so I think the easiest thing to do would be write it like this. And notice that this here is going to be En naught complement as desired. For the simple reason, R is the disjoint union of all of these. So yeah, it's if you really want to prove this, by all means, do it yourself. That the complement of En0 is this disjoint union. It just follows almost trivially from this. And that's all we need to do. So I'll keep forgetting that. Yeah, keep forgetting the outer measures. Yeah, okay. Any questions here on anything this problem? So really just countable subadditivity and using what you're given. Prove exactly what you want, and yeah. All right, so no questions on 2. Okay, 3. There's 2 ways to do this. I always forget to when I have this kind of problem in mind, I always forget to mention this. So this is like the easy part of the proof of Egorof's theorem. So it's ridiculous that sometimes Egorof's theorem's proof is asked on the prelim, but this is much more manageable to prove the easy kind of part of Egorof's theorem. On the other hand, you can use Egorof's theorem to very easily do this. Kind of what I was thinking is, prove the easy part of Egorof's theorem. So I did not say don't use Egorof's theorem, but if I put it on again, I probably will say don't use Egorof's theorem. So if you did, and you did it well using Egorof's theorem, you got that right. So I'll do it both ways, using the hint and using Egorof's theorem. But yeah, just understand it's a bit, well, it's very circular to use Egorof's theorem to do this, because the point is this is part of the proof of Egorof's theorem. Okay, so number 3. Yeah, and actually doing it from scratch, just using continuity of measures, not that much longer. It's a little longer, but it's not that much longer. So I'll cover up the hint because I don't need it right now. Okay, so yeah, using Egorof's theorem. There exists an A subset of E, where Fn goes to F informally on A. I'm going to use this delta here. I don't really need the, I guess this is zeta or eta. I guess it's eta. So I did it like just like it is in the book. I do have the book here actually, but I'm not going to pop it open. But, yeah, so that's why I picked the letters here. Yeah, sorry. So this is going to be less than delta. I can pick whatever I want here. The problem asks for delta, so delta. And it's, sorry, there exists measurable A by Egorof's theorem. Sorry, that's all I need. All right, so we're basically done. By uniform continuity, pick big N. It does that every now and then. Yeah, just literally using the definition of uniform continuity with eta here, or zeta. And that's it. There's nothing else to do. We've, by uniform convergence, we have an N and we have an A, where the measure of E take away A is less than delta, A is measurable. And this is true for all X and A as long as N is bigger than, little n is bigger than big N. So by uniform convergence, we can pick this N where this is true. So any questions on using Egorof's theorem? So should we make this a small p then? Okay, so yeah, so without using Egorof's theorem, right, so I'm assuming Fn goes to F pointwise on E. I could have said pointwise almost everywhere. You just excise the set of measure 0. So the hint is use continuity of measure, so you gotta come up with some way to use continuity of measure. So in particular, you have to have either a sequence of nested intervals or increasing intervals, sets, nested sets or increasing sets. So I think the easiest way to do this, or at least the way I did this, is let's say we have something increasing and the union is the whole set. So not super subtle in our choice of our sets. Now to get that this is these are increasing, I want this for all little n bigger than big N. Okay, so it's pretty clear that these are increasing, but if you have any doubts, it's no problem. Yeah, so if X is in AN, then this is true. I mean, this is pretty obvious, but it's just a sanity check. That's a nice sanity check, I think. So that's going to imply this is true for all, maybe someone can answer this, for all what? For all n bigger or equal to what? So I'm trying to prove that these sets are increasing. So if this is true, then this is true for all n bigger or equal to what? Well, n plus 1. So if little n is bigger or equal to big N plus 1, it's certainly bigger or equal to big N. It's got to be strictly bigger than big N. So kind of. Yeah, so these are getting bigger and bigger and bigger. I mean, it makes sense because we're requiring less and less and less for bigger and bigger n. Like if n is 1, this is a really strong condition. It might not be too many x in this set because this is small for every n. Right. Yeah, also by pointwise convergence, this is kind of trivial because it's just literally the definition of pointwise convergence. So I gotta down a second. So what am I getting at? The union is all of E. Sorry. Yeah, so this is less than zeta. So certainly this big N will in general depend on X. That's fine. It's just pointwise convergence. So this is true. So that implies X isn't big AN, yep. And then that says that E is going to be this union. Because we have pointwise convergence on all of. Right. Any questions at all so far? I mean, by all means, you have questions, rewatch this and then shoot me an email. Yeah, I'll send everyone who's taking the prelim in August. We'll start doing review stuff. Try to do it next week. So give you guys plenty of time to do review sessions. Plenty of review. Okay, so the continuity of measure, and if there are any doubts, Fn minus F absolute value is measurable. So this is going to be a measurable set. You can write this as the intersection, countable intersection of measurable sets. So I can squeeze this in. This would be intersection little n bigger or equal to big N. This function here of 0 to, or you can even do minus infinity eta. Right. So in particular, this is measurable. Even if you forgot that, it's not a big deal. All right, so now we're almost done. So yeah, in particular, each one of these has finite measure because the measure is always less than or equal to the measure of E. I mean, that's trivial because all of these are subsets of E. It's looking at X and E where a bunch of stuff is true. So yeah, the assumption that each one of these has finite measure allows us to use excision property of the big measure. So that means 0 is this limit here. Because this thing right here is, again, this is crucial that E has finite measure, which means all the ANs have finite measure. Otherwise, this otherwise just has no meaning, because it could be infinity minus infinity. Okay, but this one has finite measure because the measure of E is finite. Okay, now we're almost done. So just pick n so that this is less than delta, and let's say this is my A. Let's call this A. All right. So I claim we're done. If X is an A, so it's big AN, well, then this is true for all n bigger or equal to n, big N. So we're done. That's just a definition. Yeah, that's exactly what we need to do. All right. So yeah, kind of the punchline here is set up these ANs with a little bit of thought. They're increasing. Pointwise convergence on E gives me that the union is the whole set E. And membership in this for some n is really exactly what we want. Yeah. Yeah. At least for this part is exactly what we want. As long as E take away A is small, which we can pick n big enough where it is. So any last second questions before we move on to the next one? Okay, 4. Yeah, 4 is no, an easy one. Yeah, so just write this as unions and intersections and stuff. So countable operations, unions, intersections of measurable sets is measurable. So this will easily be measurable. So do this step by step. So let me first actually do this. Yeah, it's silly. If and only if for any m, there exists a big N. Where for any n bigger or equal to n, we have fn of x is bigger than n. Right? Yeah, it's exactly just 511, translating this into quantifiers. So for every m, there exists an n where further in the sequence than big N, then this is bigger than big N. So it's nice and big. So just translate quantifiers. Yeah, so how would I translate these quantifiers? We've done many times before. For all would be what? Well, intersection. There exists is union. For all is intersection. And this is saying X is in this inverse image. Fn of X is bigger than N. So yeah, this is measurable. This inverse image. It's technically another bracket. But not going to put all these brackets here. Yeah, and if you have any doubts, I would prove just carefully, one's a subset of the other if you have any doubts. But the right-hand side is just unraveling exactly this here. Again, this here is measurable. Right. Any questions here? Right. Okay, so 5, let's show that this is continuous. And the idea is just particularly show it's continuous at 0. Just calculus rules say it's continuous at all other points from 0 to 1. I mean, you don't have to really write this, but yeah, so it's x sine. Oops. Yeah, just trivial calculus rules say this is x0 sine 1 over x0. Everything is nice and continuous as long as we're away from 0. On the other hand, this is, of course, less than or equal to absolute value of x. So by squeeze theorem, so yeah, so you can say if this is true, then this is true. Fit it. Yeah, so by squeeze theorem, this is true. Right. Yeah, so this is continuous. Yeah, actually, So the point here is that it's uniformly continuous because continuity on a closed interval means uniform continuity, but it's going to fail to be absolutely continuous. So uniform continuity does not imply absolute continuity. All right. So yeah, probably a lot of different ways to do this. The easiest one is like we did in the example like a few weeks ago. So let's say Bn is 1 over 2 pi n. So these are both going to go to 0. I'm going to partition actually 0 to infinity in kind of a nice way. N 1 over 2n plus 1/2 pi. So yeah, the thing to note is the following. I'll explain why this is useful in a second. So I claim this is true. Yeah. This is the same thing as saying 1 over n, 1 over an, less than 1 over b n plus 1. Well, this is trivially true. It's 2n plus 1/2 pi is certainly less than 2 pi n plus 1. Just plug in n plus 1 here, do 1 over it. Okay, so what's the point? The point is, now obviously you have a bigger denominator for an than bn, so each of the b's are bigger than the a's, so b1 is bigger than a1. Right. A1 is bigger than b2. Et cetera, et cetera, et cetera. So B2 is bigger than A3. Sorry, that makes sense. B1 is bigger than A1. A1 is bigger than B2. B2 is bigger than A2. A2 is bigger than B3. So yeah, so we have B1 is literally 1 over 2 pi, so it's actually pretty small, but whatever. We got B1, A1, B2, B2, et cetera, et cetera. So these intervals are certainly going to be disjoint and they can't add up to more than 1. Because they're just disjoint intervals in 0 to 1. All right. Makes sense. Yeah, so the punchline here is they're disjoint intervals in 0 to 1. So you can make this sum as small as you want. Since the original sum of all these intervals, the length of all these intervals is certainly less than 1. I don't care what it is, but it's add up all these orange lengths, certainly less than 1. And in particular, it's finite. That's the important thing. It's finite. So the tail converges to 0. Right. All right, and I'm going to prove that each of the tail, even though the tails of these intervals, the sum of the length of these intervals is small, plug things into your function and actually converges to infinity. So it's not only is it not small, it's can't really get larger than infinity. So yeah, this miserably fails to be absolutely continuous. That's it as plug and chug. Just remember your trig. So it's Bn minus An, so sorry, Bn sine Bn, or sine 1 over Bn. So it's An right, so just distribute the pi. Well, this is just 1. This is just 0. Right, so yeah, this is the tail, or sorry, this is it's like the what kind of series? The harmonic series. So it's yeah, it's like the harmonic series. So no matter what big N is, sum is infinity. So yeah, we can make the sum of these lengths as small as we want. But this being small does nothing to make this small here. In fact, it's always going to be infinity. So it miserably fails to be uniformly absolutely continuous. Right, any questions here? I think, Brian, you're the only one left. Oh, no, sorry. There's quite a few of you still left. All right. Yeah, if people would much prefer, I can go back to in-person meetings. It's up to you guys, really. Okay. Yeah, number 6. I'm not gonna do that. I mean, that's been done many times. I'll just maybe in the comments I'll put a link to where, I mean, I guess I did number 5 in a video recently. I could have just pointed you to that, but 6 is done many times, so I'll give you a link to that. Yeah, let me do 7. There's 2 ways to do 7. You can just use Fatou's lemma or use the generalized Lebesgue dominate convergence theorem. So let me go to that. I always forget where that is. So I'll do that way first. They're both start off in basically the same way. Okay, so this is generalized. Okay, so it's actually a homework, so that's annoying, but it's fine. So here's 88. It's not in the index. Yeah, okay. So yeah, so this is this is the general dominant convergence theorem. So yeah, sometimes this is useful on prelim, but other times we basically ask you to prove this or prove the Lebesgue dominant convergence theorem. So one way or another, you do have to remember the Fatou's lemma trick that really proves this, and you can use for all these kinds of problems. But anyway. All right, so number 7. I'll go back to that in a second. So I'll actually go look at this real quick. All right, so you have a sequence of functions converges almost everywhere to F. Instead of one dominator, there's like a sequence of dominators in the following sense. And the key is the GN, the integral of the GNs converge to something which itself is finite. It's got to converge to something, and it's got to converge to something finite. If that's true, then this is true. Right. All right, so yeah, let me use instead of Fn, big Fn in this theorem here. So this is 7. So let's say Fn is, ultimately we want to show that this converges to the integral of this equals 0. Of course, the LP norm is the integral whole thing raised to the 1/p, so I'm not going to write that. Yeah, I need to show this. I think it's over the real line. Yeah. Okay, so yeah, I need a sequence of dominators. So you could try to get a single dominator, but there's just nothing. There's nothing dominating each Fn. Yeah, so there's not there's no one single dominator possible. The Fn's could be larger than F, smaller than F. You just have no idea. So you really can't use the dominated. You can't use a regular dominated convergence theorem. So we do the kind of same trick that we kind of do every now and then to dominate this, or to get something non-negative for Fatou's lemma, which we'll do in a little bit. So just triangle inequality. And each one is less than or equal to the maximum. That's kind of trivial. I mean, the max could either be one of them, but each one is definitely less than or equal to. You don't have to write all this if you remember that this is less than or equal to, well, if you remember doing this, you can just write it. But, so the point is, this is less than or equal to 2 times the max. Implicitly, I'm plugging in, I guess I can do that. Be clear. This is for, it's technically not each x, because these are only defined almost everywhere, but oh, whatever, you get the point. This is silly. Okay, and this is equal to 2 to the p. Well, the max is one or the other. So either way, it's the same thing as the max of these two. And the max, well, again, the max is one or the other. No matter which one it is, it's less than or equal to the sum. It's an absolute value, it's not negative. So the max here is less than or equal to this sum here. So yeah, like I was saying, if you remember this inequality in blue, that this, or even just this one here, is less than or equal to this, that's fine. You don't really have to write details because it's pretty easy. But all right, so this is my GN. Let's just check this GN works. All right, so what is yeah, sorry. So I mean, one part we checked. This is equal to Fn, big Fn. So big Fn is less than or equal to little gn. It's fine. Let's check the other part of the generalized dominant convergence theorem. All right, so this is 2 to the p times limit. Well, for this, there's no limit. It's just f to the p. And so remember that this is the LP norm of Fn bar raised to the p. So this converges to what? What's the assumption? So in this problem, we're assuming what? Well, the LP norms converge to F, the LP norm of F. So raised to the p doesn't matter, and we're assuming it's finite because, well, F is an LP. So this is finite. So this is going to be equal to, oh, sorry, 4 to the 2 to the p plus 2 to the p is 4 to the p times this integral here. It's finite. Yeah, by definition, this is LP norm of F to the P. All right. Yeah, so we're good to go. So Fn converges to, well, sorry, for us, big Fn converges to 0 almost everywhere, because we're assuming that Fn goes to F almost everywhere. So same thing as saying absolute value of Fn minus F goes to 0 almost everywhere. So finally, Fn goes to 0. Yeah, I'll just remind you, what is this? Fn minus F LP raised to the P. Going back up here. And so, yeah, Fn goes to F. The generalized Lebesgue-Dominique convergence theorem says I can interchange limits and integrals. So my sort of like, it's like my little f is sort of 0 here. So it's like, sorry, there's no E here. So you see these kind of problems on general E. All right. So the Fatou's lemma kind of proof, we still need this inequality here. So this is using a generalized Lebesgue-Dominique convergence theorem. So let me just give myself plenty of room. Okay. I'm basically using Fatou's lemma, you're reproving the generalized Lebesgue-Dominique convergence theorem, essentially. But again, I could very well ask, prove the generalized Lebesgue-Dominique convergence theorem, and I would give you the hint if I did that. This is, the hint, use Fatou's lemma. All right, so yeah, from before, definitely don't want to repeat this. We have this. Of course, like with these arguments, we always need something non-negative to use Fatou's lemma. So just bring this to the other side. And F and each Fn are in LP. So on both sides, these are pointwise defined as a real number almost everywhere. So not a huge issue for the prelim, but you're not doing infinity minus infinity. So if you forget to point that out, I'm not going to care too much. Really, I'm not going to care at all, but frankly. But yeah, it's good to just be mindful of that. You actually use analysis for research. Okay, so yeah, I don't know. Guess I'll do big Fn or well, big Gn, whatever. You already used Fn. So just something for Fatou's lemma. I'll do big Gn, I guess. Okay. Yeah, so we're almost done. I guess this might even be a little quicker. So point-wise, almost everywhere, what does Gn equal? Well, Fn goes to F, point-wise almost everywhere, so the Fn just goes to F. So it's just 4 to the P, 2 to the P, absolute value of F to the P, plus 2 to the P, absolute value of F to the P is 4 to the P. This goes to 0, the Fn minus F almost everywhere, right? Sorry. So let me do it like this. So like all these arguments, the lim inf is the limit if it converges. And this is true almost everywhere. Or for almost every x and r. All right, so let's just do Fatou's lemma. So yes, so this here is the limit, integral of the lim inf. I'll write exactly what Fatou's lemma says. So this here is Fatou's lemma. Yeah, it's one of these kind of a miracle occurs converting lim inf to lim sup, and kind of gives you exactly what you want. All right, so yeah, this is just Fatou's lemma, this inequality here. This is just the lim inf is messy looking absolute value of F to the P. All right, so now, well, just what is Gn? It's this whole thing here. I'm gonna need more room. Okay, so it's a lim inf of 2 to the P integral Fn to the P, and we're assuming that converges to absolute value, the integral of absolute value of F to the P. Here, let me do it like this. All right, so minus integral here. Right, so again, the assumption here is that Fn norm, LP norm converges the norm of F, so raise it to the P. This is going to converge to this, so this is 4 to the P. And I'll just bring this outside so it matches. Doesn't matter, it's just 4 to the P, it's just a constant. Lim inf minus of the lim inf is minus the lim sup. All right, so yeah, we cancel these out because they are finite by assumption. F is an LP. Sorry, F is an LP here. So that means the lim sup is less than or equal to 0. So it has to be 0. So the lim sup is less than or equal to 0, means the limit itself. So it's not negative, so the only way for it to be less than or equal to 0 is if it's equal to 0. Yeah, I'm just trying to bring this to the right-hand side. And so that's the same thing as saying, because it's not negative, that the limit is 0. Got the p's. Yeah, so any questions on either of these ways of doing it? All right. Yeah, now the next one is quick. The last one. I've done this quite a few times or in lecture. Forget if it's homework. I don't think I ever made it a homework. So yeah, just prove that the L infinity norm is itself an essential upper bound of your function. So E is measurable, F is a measurable function, essentially bounded. The L infinity norm is the infimum of all these essential upper bounds. Essential upper bound meaning absolute value of f of x is less than or equal to lambda for almost every x. Yeah, it's not trivial that it is an essential upper bound, so that the inf is actually a minimum. That's what we're trying to prove. So just play with the definition of inf. That's really so I forget what I called this in lecture, doesn't matter. Let's say U for essential upper bounds. All right. Yeah, so this is just the infimum of U. Right. Yeah, this is non-empty. We're assuming F is essentially bounded. It's obviously bounded below by 0. There's just positive stuff in here. Right. Okay. Yeah, so look at this plus 1 over n. So it's not so this is the inf here. So this is not a lower bound of U. So pick U. Sorry, pick let's call it lambda n, where well, let's just do the definition. So usually it's less than or equal to if at the lower bound. So it's not. So this is going to be bigger than lambda. All right. So what good does that do? Well, this is true for almost every because lambda n is an essential upper bound, but it's in the set of all central upper bounds. And lambda n is less than the L infinity norm plus 1 over n. So in particular, this is true. Right, so let's say an, whatever you want to call it. Yeah, I guess I'll do an. So let's just kind of remind you of what this means. So if this is settle x in E, or this is not true in green. Well, this has measure 0. That's what it means for this to be true in green almost everywhere. Set where it's false has measure 0. All right, so the usual, take the union. So each has measure 0. So this has measure 0. Yeah, and we're almost done. I mean, this is going to give me that the L infinity norm is an essential upper bound, because if we're away from A, well, E take away A is just the intersection of the E take away ANs. E take away union is the intersection of E take away each set. So, well, that means this is less than or equal to absolute value of L infinity norm of F for each n. So we're away from all of these. So that means this is less than or equal to absolute L infinity norm of F. Okay, so the conclusion is the set here. We want to prove that this has measure 0. And it does because it has to be an A. Because if we're not an A, then the opposite inequality is true. So we basically proved A complement is a subset of this complement here. So it's the same thing. So this has measure 0. Since this has measure 0, the measure of A is 0. It's a subset of A. Okay. Yeah, maybe in the future it's better to do this in person because this is even tiring me out on Zoom. And someone can record it. I'd be happy if someone records it. I'd be thrilled if someone records it so I don't have to record it. Yeah, if anyone wants to record it on their laptop, set it up, by all means, they can do that in the future. Well, yeah, anyone has any questions, let me know, or email me when you go through it. Yeah, I'll put this up. I'll send everyone an email when I do that. Should be pretty soon today. So, all right, I'll have a great weekend.
Yeah, likewise.
Yeah,
Thank
I'll
you.
see you guys probably pretty soon. So it's probably better to start studying sooner than later. So,
Sure. Have a great weekend.
yeah, too. Take care. Bye.